some theorems on number theory. But first, you need to understand the concept of congruence modulo, where we speak about the congruency of two integers instead of the triangles concept. Okay, so here two numbers are congruent if they leave the same remainder when divided by another number n. So here n is 6, and when 1 is divided by 6, it leaves out a remainder of, okay, sorry, excuse me, it when 7 is divided by 6, it leaves out a remainder of 1. Similarly, 13 when divided by 6 leaves out a remainder of 1, so it is congruent to 13. 13 is congruent to 7. Okay, now there are a few basic properties of modulo, so I will just write them down and I will explain you. Since on the computer, on the laptop, we cannot write the congruency operator, I'll just use the equal to sign instead of this operator. Okay, just that's the thing you need to keep, but usually it is like this, 3 stripes. Okay, so basic properties of modulo bases are that if A is congruent to B mod M and B is congruent to C mod M, then A is congruent to C mod M. Okay, so there is a proof of this. We'll come up with the proof in the next video. Okay, next, if A is congruent to B mod M and C is congruent to D mod M, then A plus C is congruent to B plus D mod M. If A is congruent to B mod M, then A plus K is congruent to B plus K mod M. If A is congruent to B mod M and C is congruent to D mod M, then AC is congruent to BD mod M. Okay, and the most important one, if A is congruent to B mod M, then A to the power n is congruent to B to the power n for mod M for any natural n. Okay, and if AC is congruent to BD and BD mod M and GCD of C and M is 1, then A is congruent to B mod M. Again, let's take some examples now. So just solve these questions first, and when you're done, you should yourself understand the question. Okay, so just solve these questions, take your time, and let's move on to the next topic now. So the first theorem is, if P is a prime, then A to the power P is congruent to A to the power A base mod P. Okay, so for example, 30 raised to the power 31 will always give out a remainder of 30 when divided by 31. As simple as that. Okay, let's move on to the next one. Now, if P is a prime, then n to the power P minus 1 will be congruent to 1 mod P. For example, 30 to the power 31 minus 1, which is 30 to the power 30, will always give out a remainder of 1 when divided by 31. This can again be proved like, say, I'll show you the proof of this. 30 to the power 30 is basically congruent to minus 1 mod 31. Now we can write this as 30 to the power 30 is congruent to minus 1 to the power 30, which is basically minus 1 square to the power 15. But basically minus 1 squared is 1, so 1 to the power 15 is 1. Now 30 to the power 30, if it's congruent to 1 mod 31, our thing is proved. This was a pretty easy one, to be honest. Okay, now let's move on to the next one. By the way, this is called Fermat's Little theorem. Okay, this is used lot of times in IOQM. In fact, it was used in 2 questions in IOQM 2025. Now again, if p is a prime, then n to the power p is congruent to n mod p. This is the simple most topic, okay? Now the next one is Wilson's theorem, okay? Okay, to understand this, you must know what a factorial is. In mathematics, a factorial is shown by the exclamation mark sign or just two lines making an L shape below the number. So you write the number here and you write the exclamation mark after it. Okay, you can use either of the signs. Mostly we use the exclamation mark sign. Okay, for a positive integer n, the n factorial is just multiplication of n into n minus 1 into n minus 2 up till you get the last two as 2 and 1. So basically last one should be 1 and not 0. Also, one thing should be noted that 0 factorial is always 1. That's it. Next, let's move on to Wilson's theorem now. Okay, so Wilson's theorem says that if p is a prime, then p minus 1 factorial plus 1 is always congruent to 0 mod p. Now this can be proved again. So if we put the smallest prime, which is 2, in as p, okay, so 2 minus 1 factorial plus 1 is congruent to 0 mod p. Now p minus 1 factorial, which is 2 minus 1 factorial, which is 1, 1 plus 1 is congruent to 0 mod 2, because 2 plus 0, 2 is congruent to 0 mod p, because there is no remainder when you divide 2 by 2. Okay, the quotient is 1, but the remainder is nothing. The remainder is 0. So you can prove it by any which ways. There are many mathematical proofs on this. Okay, we can make another theorem from Wilson's theorem, which can be derived from our property that A, okay, so if A is congruent to B mod M, then A plus K is congruent to B plus K mod M. Yeah. Now again we can write this as P minus 1 factorial plus 1 is congruent to 0 mod M. But if we subtract the 1, what we get is mod M. Simple as that. Now this is quite useful, okay? Now there are questions like mod P. Sorry, my bad, okay? This should be mod P, because P is always prime, okay? So 97 is a prime number, I guess. Wait, let me check. Yeah, if 97 is a prime number, then 97 minus 1 factorial would always give a remainder of minus 1 when divided by 97. Okay, for example, 96 factorial would give us a remainder of minus 1 when divided by 97. That's it. That's all for this theorem. Now let's solve some questions. Okay. Okay, so the first question is 9 to the power 9 to the power 1990 is congruent to question mark mod 11. Can you find out this? Write the answer in the comments, as I can only check there. Okay, so the next, okay, so write the answer in the comments and I'll check the answer. Okay. So these are the only two questions we're gonna do today, and we will increase the intensity as we go further in our topics. And again, there is Fermat's last theorem, which says that a to the power n plus b to the power n will always be is equal to c to the power n, but there is no solution for n greater than 2 and a, b, c are positive integers. Okay, you can try to prove it by yourself. And yeah, c to the power n cannot be 0 as well. Okay, that's it. Can you tell me the prime factorization of 24? Yes, you obviously can, but can you tell me the number of factors of 24? Now see, you can count it, but what if I and you will get to a solution of 8 factors of 24? But what if I give you a number like this? Now tell me the number of factors of this number. Will you be able to tell it in seconds? No, right? But with one simple theorem, you can tell the number of factors of any given number if you can prime factorize it. Okay. And if you know the fact that composite numbers have a distinct prime factorization, which is made up of primes and they are raised to some power. Okay. Now that is a completely different topic which comes out from the fundamental theorem of arithmetic, which you okay. Okay, so a composite number is in the series A is equal to b to the power n plus c to the power m, where b and m are primes and a is a composite number. The number of factors it has are n plus 1, m plus 1, n plus 1 into m plus 1. Here it is 3 plus 1 into 1 plus 1, which is 8 and 24 has 8 factors. Okay, so there's another trick for finding out the prime factors of large numbers which have a 0 in their end. You can split it always in the form of 2 into 5 to the power n or m, anything. So it will always be like that, because if n is 1, n equals 1, then it will be 10. If n equals 2, it will be 100. If n equals 3, it will be 1000. As simple as that. Because okay, 2 into 5 is 10, then 2 into 2 squared into 5 squared is 4 into 25, and simply that's it. Okay, so next we will study the properties of division and division algorithms, which we have previously learned, which is Euclidean division algorithm. But now we will learn the actual meaning of divisibility and what's beyond mathematics. Okay, so that was all for today. I'll make the next video on the next weekend, so stay tuned.